I'm Hans Forsström, and I'm a senior advisor at SKB International. I have for many years been involved in the development of the Swedish radioactive waste management system. And I've also been a director at the IAEA for radioactive waste management. Today I will talk to you about a study on low and intermediate level radioactive waste management in Estonia, which has been performed by SKB International. I will start by talking about what is radioactivity and where does it come from. When you look around, most of what you see around us is built from stable atoms. This oxygen we breathe, the carbon we eat, etc. The radioactive atoms, the radionuclides as we call them, have an excess of energy and wants to become stable. They decay by sending out radiation, which could be harmful for human beings. They do that with what is called a half-life, that is, how long time it takes for half of the radionuclides to disappear. And this half-life could be between microseconds and hundreds of millions of years. Some radioactive atoms exist in nature or are created in nature. For instance, uranium was created in the stars and has a very long half-life and still exists. And some of it has decayed into radium. Another is carbon-14, which is generated from cosmic rays in the atmosphere. What I'm going to talk about mainly is those radionuclides which are created in the nuclear reactors. For instance, cesium-137, cobalt-60, or plutonium-239. Most of the radioactivity in a nuclear reactor is generated in the nuclear fuel. It's more than 99%. It's created by the fission process and by activation, and it stays in the fuel. The fission process, which you see on the left-hand side of this slide, is the process which generates the energy. It starts with that a neutron hits a heavy nuclide, for instance, uranium-235, and it splits into two smaller or lighter elements, fission products. It also, in this process, is generated 2 to 3 neutrons, and one of the neutrons is hitting a new heavy element, and it keeps the chain reaction going. That is where the energy is being generated. The other neutrons could hit other material, for instance, iron in the water around the reactor and produce cobalt-60, or could hit a uranium-238 atom in the fuel and create transuranic elements like plutonium-239. The most important thing is most of the radioactivity stays in the fuel. Now, why is radioactive waste dangerous? And what is the purpose of the radioactive waste management? Well, the risk of the radioactive waste depends, of course, on the activity level and the physical form in the particular waste package. The risk one is the direct radiation from the waste package, which you protect yourself from by shielding the package or by handling it remotely. But you also have the risk for release of radioactive particles and uptake by that you eat it or you inhale it, you breathe it. And in order to avoid that, you actually make sure that the waste is in a solid form. The purpose of the radioactive waste management is to protect man and the environment from exposure to radiation and or ingestion or inhalation. This is done by containment. You keep it in a package, remote handling or shielding in order to shield yourself from the direct radiation, and then you have the waste is solidified and packaged so that the radioactive particles will not come loose, and you dispose of it in engineered facilities on the surface or underground. And once you have disposed of it, it's not a direct radiation which is on concern, but that the radioactive elements stay in the package. Radioactive waste comes in many different configurations and with very different activity levels, ranging from coveralls or discarded equipment, which is low-level waste, to the spent nuclear fuel, which is long-lived and has a very high content of radioactivity. It's therefore necessary to classify the waste as low-level waste, intermediate-level waste, and high-level waste. And in this presentation, I will concentrate on the low and intermediate-level waste. The source of the radioactivity in the low and intermediate level waste comes from the water which circulates through the reactor and cools the reactor. And this water can have radioactivity in it from activation, or that some radioactivity has leaked out of the fuel. The water is continuously being cleaned in filters and in ion exchange resins. And this is the process waste from the reactor. During the maintenance of the reactor, which normally is done once a year, you exchange components, you clean the reactor, and you make overhaul of different machines. From there you get waste like components, equipment, and rags and coveralls. Once the power production has stopped, it's time to dismantle the reactor. And some of the parts of the reactor are contaminated with radioactivity, and that needs also be taken care of as radioactive waste. Now, how is the low and intermediate level waste managed? Well, the first and most important thing is you should minimize the amount of waste to be generated. You shouldn't bring material into the reactor building which you don't need in there, because once it's in there, it's called radioactive waste. For instance, packages should be removed before you go in. Then you take the waste which has been generated and you collect it and you keep it segregated so that you don't mix different types of waste. You keep it segregated so you can treat it in different ways. The treatment normally being used is that you concentrate the waste into smaller volume, you compact it in a compaction. In some cases, for paper waste, for instance, you can incinerate it. And then you take the compacted material and you condition it by mixing it with cement or by mixing it with bitumen, which is an asphalt. And then you package it in a drum or a container. On this slide, you see examples of waste packages which are being used in Sweden, ranging from steel drums to large steel containers, normal shipping containers. The latter, the shipping containers, can be used for waste with very low activity and which doesn't need to be solidified, while the steel drums or the concrete molds are used for ion exchange resins, which needs to be solidified before you put it into storage. Once you have solidified and packaged the waste, it normally has to go to an interim storage facility. And on this slide, you can see an interim storage at Ringhouse, where the packages are handled with a shielded forklift truck. Then it's being transported to a disposal facility, which could be close to the reactor or far away. And the picture shows the Swedish transport system with heavy containers. And the final endpoint of management is disposal. And this endpoint determines the needs for conditioning and packaging before disposal. Now to the disposal of the low and intermediate level waste. There are two types of disposal facilities used in the world. One is a surface repository, which is used in many countries, for instance, in France, in Spain, and it's planned in Lithuania. And the other one is that you actually build a repository in rock caverns, which is what has been done in Sweden, in Finland, and is planned for Germany. And rock caverns could be in clay or it could be in hard rock. For the surface facilities, and you see here the example from the Centre de l'Aube in France or El Cabril in Spain. Essentially what you do is you build a house on the ground with thick concrete walls. Then you put the waste, as you can see on the right picture here, in these buildings, and you surround it by concrete. You cast the concrete lid on top of it, and once you have filled it, you put a impermeable material on top of it, and you cover it with grass, as can be seen on the bottom slide here. If you instead are using a rock repository like the SFR at Forsmark in Sweden or the VLG at Olkiluoto in Finland, you build rock chambers, and in the rock chambers you build concrete structures where you put the waste in a similar way as you do for a surface repository. And you also then cast concrete, grout concrete around it to make it stable. Both the surface repository and the rock chamber repositories can fulfill the safety requirements, and they are licensed in France and in Sweden or Finland. The difference is that in the surface repository you have a period of about 300 years where you control the drainage water and repair the facility if it's needed. In the rock cavern repository, you essentially close the tunnels, and then you let the low water flow in the rock make sure that the radioactivity stays. An important point both for the surface repository and the let's say shallow rock cavern repositories are that it's a limited quantity of radioactivity in the waste, especially long-lived waste. If there is more long-lived waste, which is the case for some of the intermediate level waste, there is a need to build the repositories at greater depth, more similar to what is needed for the spent nuclear fuel. For Estonia, with 4 SMRs, a total volume of low and intermediate level waste will be about 20,000 cubic meters. 60% of this will come from operation, and 40% will come from the dismantling of the reactors. Most of it is really low-level waste, and only a small part is intermediate level waste and needs deep disposal. For this, there are two possibilities for building a repository. You either make the surface repository like in France, or you make a rock cavern repository like in Sweden and Finland. Where this can be done, should be done, depends on the geological conditions. And there are advantages if you could locate it close to the reactor site, which normally in Estonia would mean that you would have a surface repository. When you should build a repository is depends on the politics, but early start is to be preferred so that you don't need to build extra storage capacity, but also from the point of view of public acceptance, that you actually show that you're taking care of the waste. The size of a surface repository is shown as the red ring on this slide. It's about 2 to 3 football fields size, 10 to 15,000 square meters. Or it could be in 2 tunnels in a rock repository. Now comes to the question, how should the waste management be organized? Well, first of all, international regulations says that each country should be prepared to take care of its own waste. And each country should have an independent regulator. Then you have on the triangle on the right also the waste producer, which is the utilities, and the waste disposer, which is often called a waste management organization. The waste management organization could be independent, or it could be connected to the waste producer. In France and Germany, the waste management organization is an independent organization owned by the state. In Finland and Sweden, the responsibility has been put on the reactor owners to take care of and dispose of all the waste they are generating. And the waste management organization is thus jointly owned by the utilities. In Sweden, SKB is owned by the 4 utilities operating nuclear power plants. In Finland, Posiva is owned by the 2 utilities operating nuclear power plants. For the low-level waste in Finland, disposal facilities have been built at the reactor sites, and that means that it's operated directly by the reactor operator. In Sweden, it's built at a reactor site, but it's a common facility for the 4 utilities. How should it be in Estonia? Should it be utility-owned or state-owned? Well, that's a political decision. Based on the experiences in Sweden and Finland, we see a lot of advantages of putting it, making the utility own it. It's important to ensure that there is money available for taking care of the radioactive waste. Many of the activities and costs appear after power production has been stopped. Nevertheless, the costs of spent fuel and radioactive waste management, including the costs for dismantling, should be seen as an operational cost. And for that reason, it's important to build a funding system based on a fee on electricity produced to take care of the late cost, for instance, the spent fuel management and reactor dismantling. This is done in practically all countries, and the fee is typically a few tenths of a eurocent per kilowatt hour. For the low-level waste disposal, which takes place almost at the same time as the reactor is operated, it could be financed directly without funding. It should be clear also that the cost for low-level waste disposal is an order of magnitude lower than for spent fuel disposal. Now, just a few conclusions. Low and intermediate level waste from modern SMRs is similar to the waste from the existing light water reactors. There is thus experience. The low-level waste will contain less than 1% of all radioactivity which is produced in a reactor. Most of the radioactivity will stay in the fuel. Well-developed methods for treating and conditioning the low-level waste is routinely applied in the reactors today. Licensed facilities for disposal, either on the surface or in rock caverns, are in operation since many years around the world. Estonia will have to develop its own disposal facility for low-level waste. The siting of this facility will depend on the existing geology, but there are advantages if the facility can be built at a reactor site. A waste management organization should be established, and it could belong to the power company, but it could also be a state organization. Irrespective of which the financing must be assured, and it should be collected from the electricity revenues. And that concludes my presentation. I thank you for your attention.
Thank you, Hans. I see that you have joined us online for some questions, and we have a couple from the audience. So the first one, do you have any thoughts on disposal of high-level waste from the possible Estonian SMR?
Well, there is a lot of experience in the world, not least in Sweden and Finland, on how it could be done. I know that Estonia is looking at deep borehole disposal, which today is not a mature technology, but could very well be developed until it's time for you. But it all depends on what geological conditions you have in the country.
Okay, great. Thank you. Then one interesting question. How is it made sure that nuclear waste is not used as a weapon?
That's a much more difficult question. I mean, the only thing which could be of interest for weapons is the spent nuclear fuel. And it's well controlled under IAEA safeguards. It's also, if you want to extract the material, you need to reprocess the fuel. And that means building a big facility. But the most important control of that the material is not being used for weapons is the international IAEA safeguards.
Okay, thanks a lot for that answer as well. Then, what would you say are the benefits of the closed fuel cycle, or in other words, reprocessing of nuclear fuel?
Well, you go outside of what I have studied, but I can give you an answer anyhow. It's very clear. The recycling, the reprocessing and recycling means that you can utilize the uranium and plutonium which is left in the spent nuclear fuel. The cost of doing that is at present very high. And that means that, the present thinking in the world is for light water reactor not to recycle. The interesting question is if you come to using fast reactors where you can actually utilize the material, the plutonium, better, and you can utilize the uranium which remains from enrichment in a good way. That is the advantages of a closed cycle. There is also a discussion about the waste. But personally, I'm of the opinion that the issues are similar for both the direct disposal and the closed cycle.
Okay, thank you very much for that. We have many more questions, but we try to get the answers to them later. So thank you, Hans.
Thank you.